In this video, we're going to look at cavity and inflection points. There's two curves here. This one is sort of curved upwards, opening up. This one is curved downwards, opening down. And they have different concavities. Well, that is related to derivatives. Okay, so what we're going to do is we're going to sketch in about 5 little tangent lines, little short ones. We'll put one there at the bottom. They're supposed to be straight little tangent lines at various points. I'm just going to move that one down a little bit. So put one at the bottom and then 2 on either side of that. We're going to look at how these slopes are changing. Okay, so here's, imagine an x-axis here. The y-axis doesn't really matter too much. But as x increases, as we go from left to right, okay, what is happening to the slopes of the tangent lines? So right here we have a pretty negative, steep slope. Maybe if I had to estimate -4, -5 or something, it's a large negative number. Well, then the slope gets larger because this slope is only about -1. And then it continues to increase. This slope is 0. And it continues to get bigger. That slope is +1. That slope is maybe +4. So we're going from like -4, getting bigger, 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 slowly imagining tangent lines continually changing here, to about -1 to 0 to +1 to +4. So the slope of the tangent line is increasing as we go from left to right. In other words, f prime is increasing. Okay, the slope of the tangent line is increasing as we go from left to right. Okay, so that means f prime is increasing. Now the first derivative tells us that anytime we have a function that increases, its derivative is positive. And because f prime is its own function and it is increasing, its derivative is positive. So what this means is that the derivative of the first derivative or the second derivative is positive, greater than 0. I'm going to say that again. So because any function that is increasing has a derivative that is positive, and f prime tells us the slope of the tangent lines, and the slopes of the tangent lines are increasing, then f prime, the function, is increasing, and therefore its derivative is positive. So the second derivative is positive. And that corresponds to the fact that this curve is concave up. It's curving upwards. It's often common to write CCU for concave up. Okay, now let's look at the concave down function. So if we sketch in some little tangent lines here, well, that one's it's not supposed to cross the graph. Difficult to draw. Okay, so here, as x increases, so as we go from left to right, I'm not worried about the y-axis, the slope of that tangent line is a very large positive number, let's say -5 or so. And then as you travel along, the slopes decrease. That slope is maybe +2. So that's about +5, that's about +2. And then it keeps decreasing to 0, and then it becomes negative. That's a -1 slope roughly. Keeps getting steeper and steeper. That's maybe a -5 or so slope. So the slopes of the tangent lines are decreasing here. Which tells us that the first derivative is decreasing, because the first derivative tells us the slopes of the tangent lines. I'm going to abbreviate there. So if the first derivative is decreasing, then because the derivative of if a function is decreasing, its derivative is negative, that means the derivative of f prime is negative. So the second derivative is negative here. And this corresponds to the fact that that curve is concave down. often abbreviated CCD. Okay, so if f double prime of some various value, we'll just say a, that's a random x value, is greater than 0, then that means the graph of f is concave up at that point, at x equals a. Or if the second derivative at a is less than 0 or negative, then the graph of f is concave down at a. Now that's just referring to a single point, concavity at a point. You can determine whether a function is concave up or down at a single point. More often you're interested in, is it concave up or down over an interval? So if f double prime of x is greater than 0 for all x on an interval I, then f is concave up on that interval I. And if f double prime is less than 0 or negative for all the x values in an interval I, then f is concave down on that interval I. Okay, so let's put this all together here and sketch a curve that meets 4 different curves actually that meet these 4 different requirements. So in the first one, we want to sketch just a little piece of a curve such that f prime is greater than 0 and f double prime is greater than 0. Well, if f prime is greater than 0, that tells us f is increasing for the function, and if the second derivative is greater than 0, that tells us that the function is concave up. So if it's increasing, it has to be going up as we go from left to right, okay, but that's straight, it doesn't have any concavity. If we want it to be concave up and increasing, we'd have to give it a little curve about like that. So make sure you pause this video and try the other 3 on your own and then play to check. Okay, if f prime is greater than 0 and f double prime is less than 0, well, if f prime is greater than 0, then f is still increasing. But if f double prime is less than 0, that means f is concave down. So it has to be increasing or going up, but curve downwards. So it'd have to look about like that. Next, if f prime is less than 0, f is decreasing. And if f double prime is greater than 0, f is concave up. So if it's decreasing, it's going down, but it's concave up also, so we'll give it a little curve upward. And if f prime is less than 0, f is decreasing, and if the second derivative is also less than 0, f is concave down. So that would look something like that. Now let's practice. Let's sketch the graph of a function that is decreasing and concave up on the interval from negative infinity to 2, and decreasing and concave down on the interval from 2 to infinity. Now notice there are no y values specified, so they could be anything really, but it's decreasing everywhere, decreasing all the way from negative infinity or before 2 and after 2, so it's always decreasing, but we're going to make it change from concave up from negative infinity to 2, so I'm just going to sketch it in here. I'm not paying any attention to my y values. There's 2, and then now it's going to be decreasing and concave down after 2, so it would look about like that. An inflection point is a point where the function changes concavity. So it is a point where the concavity changes. And let's look at these 3 graphs right here. So in the first example, the second derivative goes from being negative to positive. And it changes right here at this point P. So over here the second derivative is negative because it's concave down, and it changes to being positive where it's concave up. So that change must occur where the second derivative goes through 0 because it goes from being negative to positive. Okay, here the second derivative is negative because it's concave down, and it changes to positive because it's concave up over here. So this is an inflection point. However, the second derivative actually is undefined at that particular inflection point because the first derivative is undefined at that inflection point, which is because it's got a vertical tangent line. And in this last example, it changes from concave up to down, meaning the second derivative goes from positive to negative at roughly this point P, and this is one where the second derivative would equal 0. And those are the two kinds of places where concavity can change, or where inflection points can occur. So inflection points of a function can occur where the second derivative equals 0 and where the second derivative is undefined. Okay, some people call these hypercritical values. Sort of like critical values, but we're referring to the second derivative here, so hypercritical values. Okay. Another thing to be aware of is that concavity of a function could also change at discontinuities. So if you have, for example, a rational function that maybe has an asymptote or a hole, you would also need to check to see if concavity changes at those places. Although if a function is undefined at a point, you certainly can't have an inflection point there. So inflection points are points on a function where the concavity changes, but the concavity could also change at places that are where the function is undefined. Okay, let's put all this together and sketch the graph of a function f that has these characteristics, where f prime of negative 3 equals 0, f double prime of negative 3 is less than 0, and f of negative 3 is 8. Okay, all of those values correspond to x equals negative 3. All of these three values correspond to x equals 9. At 9, we want f prime to equal 0, the second derivative to be positive, and f of 9 to equal negative 6. And then at 2, we want the second derivative to equal 0 and f of 2 to equal 1. So first we need an axis. We're going to approximate here. So the x values I'm interested in go from negative 3 to 2. Perhaps I'll move the y-axis over a little bit. I mean negative 3 to 9. And you'll want to go a little bit beyond negative 3 for this. I'm going to take it out to about negative 7. There's 2, 3, 4, 5, 6. There's 9. We'll go a little bit beyond that. Okay, so we want f of 3 to equal 8. So that's that point right there. Okay, so I have done that. We want f of 2 to equal 1, so that's about right there. Okay, I've done that. And we want f of 9 to equal negative 6. So that's roughly right in there. Okay. Now let's look at the first derivatives next. We want the first derivative at negative 3 to equal 0. So that means that the slope of the tangent line is going to be 0. So I'm just going to sketch in a little tangent line there. Not sketching the function yet, just the tangent line. And also f prime of 9 should equal 0, so let's sketch in a little tangent line, horizontal tangent line there as well. And then the remaining three pieces have to do with the second derivative. So we want the second derivative at negative 3 to be less than 0. So that means that we want f to be concave down here at negative 3. So it's going to have a downward sort of curvature to it. Then at 9, we want the second derivative to be greater than 0. So we want the function to be concave up here. And at 2, we want the second derivative to equal 0. So that's likely going to be an inflection point. So I'm going to try to fill it in here, curving it down, down, down. And that's roughly my inflection point. And now I'm going to curve it slightly upwards. And there is a graph of a function f that meets all of those requirements. Next, let's look at this function. F of x equals negative x cubed minus 3x squared plus 9x plus 12. We're going to use this function to find some information about the second derivative. So first we're going to find the hypercritical values where the first derivative equals 0 and doesn't exist. So to do that, second derivative, 0 doesn't exist. So to do that, we do need to compute first the first and second derivatives. So we'll start by computing f primes. So we'll have negative 3x squared right here minus 6x plus 9, and then the derivative of 12 is 0. Let's go ahead and take the second derivative there. Negative 3 times 2 is negative 6x minus 6 is that derivative, and that derivative is 0. Well, this second derivative is a simple linear function, so that's going to exist everywhere. So there are no hypercritical values that come from where it is undefined. So instead we'll set it equal to 0 and solve for x. So where does 6 equal negative 6x? Dividing both sides, we get x equals negative 1. You can label this a hypercritical value, or I'm going to actually call it a potential inflection point. We don't know for sure until we determine whether or not the concavity changes at that point. Next, we're going to find a table, or make a table, to find the intervals on where f is concave up or down, and we're going to use this potential inflection point to do that, because this is a polynomial, so we already know that it's a smooth continuous curve, so there are going to be no asymptotes or anything like that. And apparently the only potential place where it could change concavity is right here at x equals negative 1. Everywhere else it's either concave up or concave down on either side of negative 1. So what we're going to do is make a table. We will put all the potential inflection points, and if there were any discontinuities in f, we would also want to put these on the table to see, to find places where f may change from up to down. Okay, now that splits the x-axis into two subintervals, from negative infinity to negative 1, and from 1 to infinity. So we're going to choose a little test value within each of those intervals. So if I choose, let's say, negative 2, okay, that's in that interval. And how about, oops, I meant to put a negative there, about 0 is in the interval from negative 1 to infinity. And what we're going to do is plug those into f double prime. So we're going to take here f double prime of negative 2 and see if it's positive or negative. So f double prime of negative 2, if I plug in negative 2 here, I've got negative 6 times negative 2, that's positive 12, minus 6 is positive 6, so it's greater than 0. So the second derivative at negative 2 is positive, which tells us that f is concave up at negative 2, and therefore it must be concave up all the way from negative infinity to negative 1. Okay, if we plug in 0 into the second derivative, here's my second derivative. Negative 6 times 0 is 0, minus 6 is negative 6, that's negative. So the second derivative at 0 is negative. Therefore the function is concave down at 0, and since negative 1 is my only place where it can possibly change from concave up to down or vice versa, the function must be concave down for the entire interval from negative 1 to infinity. So now let's use this information to determine where any inflection points occur. Okay, so because we know that it does in fact change right here at negative 1, okay, we do then have an inflection point at x equals negative 1 because it changed from up to down. Had it been concave up on both sides or concave down on both sides, there would be no inflection points. And then to find the coordinates of any inflection points, we just plug negative 1 into the function. So find f of negative 1. So I can't fit it all on the screen at the same time. Okay, so the negative of negative 1 cubed. So the negative of negative 1 cubed minus 3 times negative 1 squared is going to be minus 3 times 1 plus 9 times negative 1 plus 12. So let's see, this becomes negative 1 cubed is negative 1, the negative of negative 1 is positive 1, then we have minus 3, minus 9, plus 12. Let's see, 1 minus 3 is negative 2, minus 9 is negative 11, plus 12 is 1. And then you can put this information together with what was found in a previous video to sketch a graph of the function. So this is information that was found in a different video about the same function. We found critical values and we got x equals 1 and negative 3. So let's flip back over and write that down. So we found that this function had critical values at x equals, let's see, we had 1 and -3, and let's see if we found those corresponding y values. Yes, we did. F of 1 equals 7 was a maximum. So f of 1 equals 7 was a relative maximum of the function, and f of -3 equaled to -15, which was a relative min for this function. Let's see, then we found that the function was decreasing on the interval from -infinity to -3. And it was also decreasing here from 1 to infinity and increasing in between those values. From -3 to 1. Okay. I believe, yes, that's all that we found. Okay. So now we want to put all of this information together to sketch a decent graph. So we know that it has an inflection point, and I didn't fully write it out, let's write that. It has an inflection point at the point -1, 1 as well, and we know that it is concave up on the interval from -infinity to -1, and we know that it is concave down from -1 to infinity. Okay. So putting all that together, the largest y value I'm going to need is 7. The smallest y value I need is -15. And then all of my important points happen between -3 and +1, it looks like. So let's draw our axis about like so. So I want it to go up to 7 and down to -15. Those are, of course, negative. Okay, my x values, I'm going to stretch them out a little bit more. Let's go 1, 2, 3, 1, 2, 3, 4, 5. Okay. So let's plot the points that we know. We know it goes through the point -1, 1. Let's do this in, let's say, pink here. And we know it goes through the point 1, 7, and that is a relative maximum. And we know it goes through the point -3, -15. So that's a max there. This is an inflection point there, and -3, -15 is right about in there, and that is a min. Then we know that the function is, let's see, I can fit it all on the screen. Here we go. Decreasing and concave up from -infinity to -3. Okay, then it's increasing and concave up from -3 to -1, right? Because it's increasing all the way from -infinity to -3. So it is, what did I say, decreasing and concave up. So I'm not going to sketch it too far here. I don't know what the x-intercept is right now, but I know it's decreasing and concave up. And then it's increasing from -3 to -1, and it is also concave, let's see, up on that interval also. I think I may have previously stated that incorrectly. So it's increasing and concave up from there to there. Then we know that it is, let's see, increasing from -3 to 1. So it's still increasing, but the concavity changes between -1 and 1, and now it's concave down. So it's increasing and concave down, and then it is decreasing after 1 and also concave down. So there's a decent graph of the function, without ever touching a graphing calculator.